Hello, I wanted to go over with you some concepts related to mirrors, in particular spherical mirrors. I'm going to do a two-part video. The first video will focus on spherical mirrors, and the next video that I do will be on thin lenses. They both use a lot of the same principles and ideas, so I thought I would just do a two-part video on mirrors and lenses. So let me share my screen, and I'd like to show you the simulation that you will be using for your lab this week on geometric optics. My cat. I'm going to silence my phone. So let me share my screen and I will bring up the lab. Okay. So in the lab, there's two sections you can click on. One of them is for lenses and one of them is for mirrors. Let's first go over the one on mirrors. And we're going to discuss spherical mirrors. And this first mirror that I'm showing here is a concave mirror. If you click up here, this is considered a concave mirror. And by concave, that means that the reflective side of the mirror is on the inside of the rounded part. Okay, so this is part of a spherical shape, and the reflective part is on the inside of the sphere. And you can choose different objects to put in front of the mirror. I'm just going to choose arrow. And right now I have the light off because I want to show you what happens to this when we turn the light from the object on. Now the object doesn't have to be emitting its own light. It can be reflecting light from other sources. So this could be really anything sitting in front of a concave mirror. And I'm going to zoom out actually because I want to show you something. If I take this object and I put it really far away from the concave mirror and I turn the light on, what do you think is going to happen to the light that hits this mirror and reflects off of it? Let's turn on the light. Notice that the light from the object, and it's just showing one piece of the light. These are just a few rays emanating from the object. But in reality, there's an infinite number of light rays that are bouncing off of this object and then that are coming towards the mirror. We're only showing a few of them just to help us visualize what's happening. So notice that the rays that are coming in from really far away, they hit the surface of the mirror, and most of the rays you can see are pretty much coming in parallel to each other. So when an object is really far away from the mirror, the rays come in almost parallel to each other and they reflect off of the mirror because the mirror is a very shiny silvered reflective surface. So they are just going to reflect right off, and the light rays are going to converge at this point right here. And this point is called the focal length of the mirror. This is where all of the light rays converge if the object is really far away. So for example, if this was the sun and you were holding a concave mirror and you know everything was lined up, all of the light rays coming really far away from the sun would reflect off of that mirror and converge at this focal point. And you would notice that it also gets really hot and could potentially burn. But that's what we define to be the focal length of the object. It's where all of the light rays converge if the object is really far away. And it turns out that the focal length is actually 1/2 the radius of curvature of the mirror. So you can see that this mirror is basically part of a spherical shape, right? It's curved, and so the radius of curvature of this particular mirror is 180 centimeters. If I measure the focal length, and I'll zoom in, the focal length is 90 centimeters. So it's half the radius of curvature of the mirror. and that works for both concave and convex lenses. So now the question is, what happens if you put the object nearby the mirror? What do we see happening for a concave mirror? I'm gonna share my screen again, and I'm going to bring up my whiteboard so we can go through the definitions of things. Okay. So we're going to use the conventions that the letter P represents where the object is located in front of the mirror. So this is the object location, and it's usually in centimeters or meters in front of the mirror. And we are going to call Q the location of the image location. Where is the image located that is created by this mirror? And the other important concept here, like we just saw, was focal length. So we're going to denote F as the focal length of the mirror. And the book goes through and derives the lens equation for you. And the lens equation is that 1 over the object location, P, plus 1 over the image location, Q, is equal to 1 over the focal length. I won't derive this here. It's kind of complicated. If you're very curious, you can look it up in the book. But for spherical mirrors, this would be called our mirror equation, or it also works for lenses, so we also call it the lens equation as well. So this is how we can determine the location of where the image is if we know where we have placed the object and the focal length of the mirror. Another important equation that we will use throughout this is the magnification of the image, capital M. And that equation is actually equal to negative Q, image distance, divided by P, object distance. Again, I won't derive how they got this. There's some geometry involved, geometric optics, so I won't derive this. You could look in the book and see that this works out. So the magnification tells you how, if the object is increased in size with respect to the actual size of the object, if it's decreased in size. And it also tells us whether the object is upright or inverted. So I think it would be best to go through a couple examples to see how these equations play out in terms of our mirrors. So let's go back to the simulation, and we're going to start off with a concave mirror right here. And let's put our arrow, let's see where we want to put our arrow. Let's put our arrow at 140 centimeters away from the mirror. So we are outside the focal length. And let's make the object, that's about 30 centimeters tall. And let's make a prediction about where the image will be located for this concave mirror. So let me go back to my whiteboard. Okay. So we said our object was located 140 centimeters in front of the mirror. Object location is typically positive. If it's in front of the mirror, the object location will be positive. So in this case, the object was at 140 centimeters. We're trying to find out where the image located is, so we're looking for Q. And the focal length of our lens in this case was 90 centimeters. The radius of curvature was 180. So the focal length is 90. Let's just check and make sure that that's correct. Focal length is denoted with this yellow dot. It's at 90, so that's good. So let's predict where the image is going to be and then check our prediction using the simulation. Okay, so let's apply this mirror or lens equation. So we're going to do 1 over under 140. As long as all of the units are the same, you can stick with it. So if they're all centimeters, you can use centimeters. If they're all in meters, then use all meters. Okay, so I will just stick with centimeters. 1 over Q, we're looking for Q, so we will leave that there. And then 1 over the focal length, which is 90 centimeters. If I solve for Q, it's 252 centimeters. Okay, it's a positive value, so that means that it is going to be in front of the mirror. And let's determine the magnification as well. So M is negative Q, which is 252 centimeters, divided by P, which is 140 centimeters. So the magnification would be a negative 1.8. So what do all these numbers tell me? First of all, image location is positive, so it's going to be in front of the mirror on the same side of the mirror as where the object is actually located. So if these are both positive, they're on the same side of the mirror. And the magnification is negative. What does that tell me? If magnification is negative, that tells me that the image is inverted. So the image is going to appear upside down. And it's a value of 1.8. So the magnification is larger than 1. So the image is going to look bigger than the actual size of the object. So it's increased in size. Okay, so let's go back to the simulation and see if that's what we get. We're going to turn the light on now. Okay. And this is where the image is. So notice that the arrow is upside down, so it's inverted. That's what we expected. The image is on the same side as the object. So it's creating a real image here. The light rays are actually converging at this point, and there will be a real image at this point in space. And it's inverted, and it's a little bit bigger than our original object. It's almost twice as big. That's what we predicted it should be. The magnification was 1.8. So our original object was 30. It's almost 60 centimeters tall now. So it's almost twice as big, which is what we predicted. It's inverted, and it's on the same side as where the object was located to start with. So it's a real image. So that works out. That's what our prediction was, and it matches what the simulation is. Let's see what happens if I put the object at the focal length. And I'm just going to make it small to help us visualize. What happens when you put the object at the focal length is that the image is at infinity. What does that mean? Well, that just means that the image is projected a really, really far distance away. Another way I like to think about it is if in your headlights in your vehicle, there's shiny reflective surface on the back of them, and the light bulb, where they put the light bulb, is actually at the focal length of that shiny mirror in your headlight. Why? Because they want the light from the light bulb to be projected very far away, as far as it can possibly go, right? So you can see more. So that's kind of what it means. And it makes sense, again, because if I'm really far away, right, the light is all focused here at the focal length. If I put the object at the focal length, the light is projected very far away again. Okay, so that's kind of what happens when I get close to the focal length of the object. Now the question is, what happens when I put my object inside the focal length? What happens then? So let's suppose I put I'm going to turn the light off, and maybe I put my object now at 50 centimeters away. It's inside the focal length. Let's make a prediction what will happen now. So the object distance is 50. We want to figure out where is the image and what does the image look like. Is it increased in size, decreased in size? Is it a real image or is it something else? Let's go back to the whiteboard and work that out. So our object was located 50 centimeters in front of the mirror. We want to figure out where the image is located. The focal length is still 90. So let's use our lens mirror equation. 1 over 50 plus 1 over q is equal to 1 over 90, and we'll solve for q. In this case, I get a negative number for q, negative 112.5 centimeters. The magnification is negative q over p. So it's negative, q is negative 112, so I will put that here. And the object was located at 50 centimeters. So my magnification is 2.25. So what do all these numbers tell me now? Q is negative. That means that the image is located on the opposite side of the mirror than where the object was located. So the image actually appears behind the mirror. And the magnification is a positive number and it's 2.25. So the magnification is positive. That tells us that the image is upright. It hasn't been flipped, it's still up, it's upright, and it's 2.25 times bigger than the object size, so it is increased in size. So what does that look like in the simulation? Let's do it. Turn the light on and see what happens. So notice the image appears to be coming from behind the mirror. That's what we expected. Q was negative. Object distance is negative. It's on the opposite side of the object. The image is upright and it's bigger than the original object. That's also what we predicted. So When you get a negative value for the image distance, what that is telling you is that the image is called a virtual image. Notice that the light rays bounce off of the mirror, and the light rays never actually converge over here. But it does appear like they converge behind the mirror. If you extend those light rays backwards, it appears as though the light rays are coming from behind the mirror, even though there's really nothing behind the mirror. It just looks like the image is coming from behind the mirror. That's because of the way the light rays are being bounced off and diverging out like this. They never converge at a point over here. They never form a real image. They do form a virtual image, though, behind the mirror. And that image is 2.25 times bigger than the original one, which matches our prediction, and it's upright. So an example of this kind of mirror in everyday life, which you might use on a day-to-day basis, is a magnifying mirror. When you get close enough to the magnifying mirror and your face is in between the focal length of the magnifying mirror and the mirror itself, when you look in that mirror, the image that you see is behind the mirror. It doesn't form a real image anywhere, but the image forms virtually behind the mirror. And it looks bigger, right? It's magnified and it's upright. You don't see a flipped over version of yourself, you see an upright version of yourself. So this is the best example I can give for something like this is a magnifying mirror. So those are two examples for a concave mirror. A concave mirror can produce both real images and virtual images. Let's change it up and switch it to a convex mirror. Convex mirror are mirrors on which the shiny reflective side is on the outside of the sphere. So the shiny side is over here. Notice that the object is placed in front of the mirror like this, but the focal length of these mirrors are actually behind them. They never create a real image in front of them. If I put this thing really far away, notice what happens when I turn the light on. The light reflects and diverges away from the mirror. The light never converges to form a real image over here. But what it does do is that it appears that a virtual image is formed behind the mirror. And that means that the focal length is also behind the mirror. So let's make some predictions about what will happen for a convex mirror. Let's turn the light on here. Notice that no matter where I put the object, whether it's really close or really, really far away, I never generate a real image. I always only end up with a virtual image behind the mirror. So convex mirrors only create virtual images. Let's set up a situation here and make a prediction, and then we will see where the object will actually be located. So let's put the object 160 centimeters away, and let's make a prediction about where the image is and whether it's increased in size or decreased in size. So I'm going to put this at 160 centimeters away from the mirror. And I want to find image distance. The focal length of the mirror is 90 centimeters, but it's behind the mirror. So when you're doing focal length for a convex mirror, make sure that you denote it to be negative. So the focal length for this convex mirror is negative 90 centimeters. So again, let's make a prediction about where the image is and how it's magnified. Sorry. Okay, I put the object 160 centimeters away. I'm trying to find where the image is located. The focal length is 90 centimeters, but it's a convex mirror and the focal length is behind the mirror. So I want to make this focal length negative. Let's use our lens equation to find the image location. 1 over 160 plus 1 over q is equal to 1 over negative 90. Okay. And let's solve for q here. Negative 57.6 centimeters, and the magnification will be negative q, which is negative 57.6 centimeters, divided by the object location, which is 160. Positive 0.36. So what do these numbers tell me? Q is negative, so that is telling me that this is creating a virtual image behind the mirror. The image is located on the opposite side of where the object was located. The magnification is positive, so this is an upright image, but the magnification is less than 1. So that's telling me that the object will be smaller than what it actually is. In fact, it's like 0.3, so about 1/3 of the size. So let's check our prediction and see if it matches the simulation. Turn the light on. We are behind the mirror by about the amount that we predicted. The object is upright, but it's smaller by about 1/3. So originally the object was 20 centimeters tall. Now it's a little bit less than 10. So it's decreased by it's like a third of the original size. Convex mirrors always produce virtual images. No matter where I put the object, the image is always going to be behind the mirror. The best example of these kinds of mirrors are the mirrors that you see like in department stores, like security mirrors up in the corner. They give a really broad view, right? You could see a lot in those mirrors because they give a larger view. But the objects in them are really small. If you ever notice, the image is upright, but it's really small, but you can fit more in that mirror so you can see more. Other examples of these kinds of mirrors are the mirrors on your car. Your side view mirrors are a little bit convex. They give you a wider view frame because of their curvature. But on the bottom, they say objects in the mirror are closer than they appear. Why? Because a convex mirror makes things look smaller than they actually are. And so when you're looking at it, it looks like that car is really small. It must be really far behind me, right? But in reality, it's small because the mirror is making it look a little bit smaller. And it's actually closer than it appears to be in the mirror. So just a couple of real life examples of convex mirrors. So make sure that you can tell the difference between concave and convex mirrors. Make sure you can determine where the object is located, the magnification, and whether it's upright or inverted, and whether it's bigger or smaller than the actual object height. I hope this little quick video helped, and this should help you with your laboratory report as well.